Okay, good morning, everyone. First, I thank the organizers for organizing this meeting so nicely. So I will talk about an ongoing work that is, we want to look at the dynamics of a tag particle or a tracer while considering the particles along a linear chain. Okay, so this work is done with Debashish Chaudhary from IOP and Abhishek Dhar here. Okay, so to introduce what active particles are, so these are typical examples for active particles. So this is, a bacteria or a sperm cell which moves with a flagella-like thing in its environment, and and this is an synthetic active colloid. This is a genus colloid. Basically, a TiO2 colloid is coated with some AU one side, and these two sides can show a different kind of, motion to the different sides when they are exposed to the ultraviolet or green color of light on these sides. Okay, so these particles basically are can basically generate motion from themselves by taking energy from the environment. Okay, and in collective phenomena, we can see this kind of flock of birds or some bacterial colony that are forming and growing with time. Okay, so these are some typical examples of active particles which we see from microscale to in macro scale in nature. Okay. So in this context, the first computer simulation was done by basically Thomas Witzek, where they have shown that if you start with a homogeneous density of particles, but varying depending upon the number density of the particles and the strength of noise in the system, you can go from a order to disorder to order transition. Okay, so this kind of transition was basically demonstrated by these two simple equations, where basically at each time the position of the particles are updated by this equation xit, and their angles are updated by this equation, where theta t of average is basically tells you that each particle the velocity direction of each particle gets influenced by the average direction of its local neighbors. Okay, and then you have some another noise which is a temperature like variable. So you can vary the basically this strength eta and the density of the particles and see a order disorder transition in the system. And then if you see some typical examples by the collective motion of active Brownian particles, there you can see that with sufficiently high density and packing fraction and activity, they can show these kind of structures when the interaction among the particles are completely repulsive. So this is called the MIPS, or motility-induced phase transition. And this kind of structures can be found in experiments as well, when these colloids are basically illuminated by some kind of lights. So these are the phoretic colloids, and they can show this kind of MIPS behavior. Okay, so when you say about this collective phenomena, this is a kind of a phenomena that you can see macroscopically, but on a microscopic scale, you can see that if you look at the trajectories of active particles, and depending upon the strength of the activity, you can see that the trajectories, from starting from a Brownian motion, it can go up to a trajectory where it can evolve more rapidly, or it can explore more phase space in the system. Okay. And when you calculate the mean square displacement for this kind of particles, you can see that initially all of them follows a ballistic behavior that goes as t square, but at later time, it all of them follows diffusive behavior, but the diffusive, the amplitude of the diffusivity that scales with the activity parameter V0. So basically, this is called the enhanced diffusion, and that appears due to the active nature of the particles. So now to look at different kind of active particle models, there are, we consider the overdamped particle models, where dx dt is basically some activity and some external noise or thermal noise, basically eta. Okay, and the three very famous models or very familiar models are the unentangled particle, where this VRTP is basically V0 sigma, where sigma is a noise basically given by plus and minus 1, and it switches with some rate alpha. And for the active Brownian particles, you can see that the velocity of an active Brownian particle is basically some active velocity times the cos theta, where theta is basically its rotational direction. And this basically changes with time with some rotational diffusion constant dr. Okay. And there is another model which is called the active Ornstein Lindbergh particle. And there you can see that the velocity has some memory term with a persistence time tau. So all of them kind of show similar kind of behavior, at least if you calculate the second moment, up to the second moment of the this noises. And there you can see that all of them are have some kind of memory term, where the memory term is given by this rate alpha for the RTP particle, where it is given by this 1 over rotational diffusion for the active Brownian particles, and given by tau for this AOUP particles. Okay, so we'll specifically look at the run and tumble particle in more detail for this interacting system. So for d equal to 1, basically, if the interactions are harmonic-like, you can solve them exactly. But for d greater than 1, the analytical calculations might be difficult, and one has to definitely rely on the numerical simulations. So if you consider the particles in 1D, you can consider a ring kind of a thing with the periodic boundary condition for the particles. And there, basically, you can use the as different methods. And in a paper by Prashant and Anupam a couple of years back, they have looked at the mean square displacement and the correlations for some kind of particles. But if you consider the interacting particles, and if you think this as a polymer chain, these polymer chains are sometimes locally pinned by some kind of potentials when you consider them in some biological environments. Okay, so we want to consider the behavior of this bulk as well as the end particles when the chain is locally pinned, but the pinning is at the only at the end particles. Okay, and this will help the system to reach to a non-equilibrium steady state. So now, before coming to the linear chain, I tell you about what happens to a single RTP when it is in a trap. So basically, for the single RTP, as I told you, the noise-noise correlation is given by an exponential decay of time with the persistence time given by 1 over alpha. And if you look at the behavior of this RTP in a trap, so this is basically in a harmonic trap, and you can see that, so basically alpha equal to 0.1 is more active compared to the higher values of the alpha. And you can see that for higher values of the alpha, the probability density has a peak near the minimum of the trap, whereas for the higher activity or the lower values of alpha, it tries to accumulate towards the boundary of the confinement. Okay, so now this is some interesting behavior that you can see at least in the single particle level also. So we want to look at how it changes when we consider the interacting chains. So for the interacting chains, we consider the model that the first particle and the, so these are the equations of motion, the overdamped equations of motion, and this first and last particle, they are with some local trap with the strength given by Kt. So we consider for the simple situation, Kt equal to K, same as the spin constant, and then we can solve the calculations exactly for the MSD and the, so basically we use the Fourier transform method, and then we look at the correlation matrix, which is given by this, and the diagonal of the correlation matrix will give you the mean square displacement for any tech particle. So MII is basically, the expression is given like this, and this is the mean square displacement for the ith particle. And then you consider when the chain is very long, and you can do some simplifications by tracing over all the diagonal elements, and then you can obtain a more simpler expression for the mean square displacement for the RTP in bulk. So basically for the mid particle, you can have an expression like this. And for any two particles, the correlation, 2-point correlations can be given by a form like this. And later we will see that using this form, we can do some analytical calculations, and we can have some exact expression for the correlation function. So now to look at the results. So this is the typical trajectories of the RTPs, where these are plotted for different values of alpha, that is alpha equal to 1.0, and more active case, that is alpha equal to 0.1. Okay, so these are some 5 or 6 consecutive RTPs, and they are evolving with time. So now to look at the mean square displacement, we have looked at the mean square displacement for different tag particles, and we have seen that for the first and the end particles, which are locally trapped, they reach the steady state much earlier compared to the particle which shows or which grows with time. And after the initial ballistic regime, it shows a subdiffusive behavior, which is T to the power half. And this is simply like the single file diffusion power law for this mean square displacement. And similarly, if you look at the mean square displacement for the for this bulk particle for different values of alpha, we can see that this T to the power half behavior is more or less persistent for all this kind of for all values of the activity, but the time scale and the crossover times changes depending upon the value of alpha, because 1 over alpha determines the crossover from the ballistic to the subdiffusive behavior.
1 minute.
So now for the 2-point correlations, we have looked at the 2-point correlations for different values of alpha. And and from the analytical expression using the Green's function, one can obtain a simple expression like for the correlation function, where this prefactor A depends upon, goes with alpha as 1 over alpha. And one can see that for increasing alpha, for decreasing alpha, basically the amplitude of the correlation function increases. And when you scale this C of X by the different system sizes, one can obtain some kind of a data collapse or the scaling behavior. And one can see that at basically X of n equal to plus minus half, it goes to the correlation function goes to the 0. Now from the correlation function, at least one can see that for different values of alpha, it scales more or less in the similar fashion. Now we look at the fluctuations for the bulk RTP, and for that we started with an initial configuration where the profile is delta function like, and we look at how it basically evolves with time. And for the higher activity or lower alpha, we can see that it spreads with time more rapidly than compared to the ones at the just a minute. Compared to the ones for the high, lower activity, or so this higher alpha limit. And one can see that, okay, at least in the long time limit, the behavior of this kind of profiles are Gaussian, but whether at small time, whether there is some deviations from the Gaussian or not. And for that, we looked at the kurtosis of this kind of distributions, and we have seen that for higher activity or lower values of alpha, one has the strong deviations from the value 0. So it has some signatures of being non-Gaussian at the lower times for the higher activities. So now, this is just a comparison plot for the bulk MSD when we consider 3 different conditions that the both ends are pinned. So we can see this data, goes to the steady state much earlier than compared to the case when one end is free and the other end is pinned. And but when we consider the particles on a ring, so basically it doesn't go to the steady state. Instead, the whole ring basically, shows some kind of a diffusive behavior, and the bulk particle also follows that. So basically, you go from a ballistic to a subdiffusive, and from there you go to a diffusive behavior, where this diffusive behavior is difficult to observe for the cases when the ends are locally trapped. So to conclude, we looked at the dynamics of a tagged particle with the nearest neighbor harmonic interactions, and we have also looked at the effect of local pinnings. So for which we considered the traps only at for the end particles, and we looked at the behavior of this bulk particle in this condition. And we looked at that the crossover from a ballistic to a superdiffusive behavior, subdiffusive behavior, but the crossover from this ballistic to the subdiffusive behavior follows a superdiffusive behavior, and that may be a little difficult to calculate analytically, the crossover time and the crossover behaviors from this ballistic to subdiffusive. And the 2-point correlations we have calculated and can be obtained exactly for using the Green's function method. Okay, thank you for your time.
Any questions?
Hello.
Yeah.
Can you go to that slide of the CX 2-point correlation? What is that correlation? Is in the steady state?
Yeah, in the steady state, yeah. That is a 2-point correlation.
But this function Cx a n by 2 minus x, this is not the function in the plot.
No, this is basically, we basically scaled C of x by n and x by n, and then we can see that at x equal to half, it goes to 0, x by n equal to half. And this decays as minus x, basically.
Okay. At x equal to n by 2, it is 0.
Yes. So that you can see from this first plot also, because this is n equal to 128 and it goes to 0 at.
Okay. Anyway, usually it's written x for x less than.
Oh, you can write it in
half like this, and yeah, okay.
Okay, yeah.
And the distribution p of x, yeah, this one. This distribution is not possible to compute analytically.
Okay, yeah, maybe possible, but yeah, I didn't try for that. But yeah, at least I tried to fit with the Gaussian form, and that fits well, at least in the late times for all of them. But yeah, okay, I don't know. Maybe
okay.
ask you later.
Thanks for the talk. I had a very simple question, maybe. You showed these MSDs in the very beginning of your talk also.
Right, yeah. Oh, that is...
It's from somewhere else, I guess. But I was curious, I mean, because we also observe something similar in experiments.
Yeah, yeah.
So why does the MSD sort of, the slope picks up to ballistic in the beginning, towards the very beginning?
This one?
Yeah. So it's not immediately ballistic. So it sort of transitions to ballistic, and after that it does other things. So do you have any idea why that could be? Or? Because in simulations, you see immediately ballistic.
You show initially ballistic and then it follows.
That's what you see in simulations, but in experiments, somehow there is also a transient to the ballistic, which I don't understand yet. I was wondering if you had some thoughts.
Yeah, I mean, this is taken from this paper, so I can also look at this paper, whether they have any explanation for that.
Let me just comment on that. There'll always be the thermal diffusion part. That'll always be diffusive first, and then the active thing, which becomes ballistic, and eventually the diffusive. That's thermal.
But without the thermal noise, you can see that, or?
This is experiment, right? So you can never get rid of them.
Maybe I can add to Vijay's comment. At very small time, it's the free particle diffusion. Each particle, they don't see that the other particles are there. And then the active things comes and it becomes T square. And the later T is because of the single file thing, I think.
Diffusion. Okay.
Okay, so let's thank the speaker again.